Welcome to This Explainer. Today, we're cracking open a brand new mathematical toolkit. If you've ever stared at a quadratic equation and thought, where do I even start? You are absolutely in the right place. We're going to build up a solid set of methods to solve these equations quickly, efficiently, and accurately. And why should we even care? Because quadratics literally govern the real world. They dictate the arc of projectile motion in physics. They help businesses maximize profit, and they even define the shape of satellite dishes beaming information across the globe. Getting the right answer isn't just a math exercise, it's how we actually understand and shape our physical world. But first, let's make sure we're working from the exact same blueprint. The standard form of a quadratic equation is ax squared plus bx plus c equals 0. Now, the single most important rule here, the absolute foundation we build upon, is that a cannot equal 0. I mean, think about it. If a is 0, that whole squared term just vanishes into thin air. And without it, the curve flattens out, and boom, you're just left with a basic linear equation. That squared term is exactly what gives a quadratic its power, its distinctive curve, and its unique properties. So, when you're working with this standard form, you kind of need to know what results to expect, right? Quadratics will always give you exactly 2, 1, or 0 real solutions. If you picture the geometry in your head, it makes total sense. A quadratic forms a U-shaped curve, a parabola. That curve might cross the horizontal x-axis exactly twice, giving you 2 solutions. Or maybe it just sits perfectly on the axis, touching it once for a single solution. Or it might just float completely above or below the axis, never crossing it at all, which means 0 real solutions. Keep that geometric reality in the back of your mind as we start breaking down the algebra. All right, here's our escalating game plan for today's explainer. 1. Simple factoring. 2. Square roots. 3. Completing the square. And 4. The quadratic formula. Tool 1. Simple factoring. Let's reach into that toolbox and pull out our very first item. Now, this is usually the fastest tool you've got, as long as the numbers play nice. The steps are super straightforward. Step 1, set the whole equation to 0. Step 2, factor the quadratic side. And step 3, set each of those individual factors equal to 0. Now, why does that last step actually work? It relies on this brilliant little thing called the zero product property. Basically, if you multiply two things together and the end result is 0, strict logic dictates that at least one of those original things must absolutely be 0. There's literally no other way to multiply to 0. It's this simple logical property that lets us crack the equation wide open. Okay, let's dive into this with a concrete example. Say we start with the equation x squared minus 5x equals 6. Following our steps, we first move that 6 over to set the whole equation to 0, giving us x squared minus 5x minus 6 equals 0. Now we need to factor it. And I really want to pause here, because this specific setup, it is a notorious trap. If you're rushing, your brain sees a 5, a 3, and a 2, and you might intuitively guess the factors are x minus 3 and x plus 2. But if you actually multiply out x minus 3 times x plus 2, you get x squared minus x minus 6. The middle term is completely wrong. The actual correct factors for a sum of -5 and a product of -6 are -6 and +1. So our factored form is correctly written as x minus 6 times x plus 1 equals 0. Set those to 0, and we get our true tested solutions, +6 and -1. Seriously, always double-check your logic here, because when simple factoring works, it is beautifully efficient. Tool 2. Principle of square roots. So what happens when an equation isn't perfectly set up for standard factoring? That's when we pull out the principle of square roots. We use this specifically when the equation has a square and a constant, but completely lacks that middle first-degree x term. Now, before we calculate anything, we have to acknowledge a strict mathematical boundary. As our source material points out, remember, you cannot take the square root of a negative number. So if this process leads to taking the square root of a negative number, there are no real solutions. Basically, if your math leads you to a negative under the square root, you stop. Yes, higher level math explores imaginary numbers to solve this, but for our practical real number toolkit today, a negative just means the parabola never touches the x-axis. Now, if you are in the clear regarding negative numbers, the mechanics here are kind of like managing a perfectly balanced scale. First, isolate your square term on one side of the equation and move your constant to the other side to balance it out. Then apply the square root to both sides simultaneously to strip away that exponent. Finally, solve for x. It is a highly satisfying, super direct method of unearthing your variable, provided the equation naturally fits the profile. Let's compare a clean, ideal scenario with a more stubborn one side by side to see how this tool performs in the wild. In example 1, we have x squared minus 16 equals 0. We easily push that 16 over, take the square root of both sides, and boom, we get a clean positive or negative 4. It's elegant and incredibly fast. But example 2 makes us work for it. We start with 2 times the quantity x plus 3 squared minus 14 equals 0. First, we isolate the square by moving the 14 over and dividing everything by 2. That gets us x plus 3 squared equals 7. We take the root of both sides and we end up with x equals negative 3 plus or minus the square root of 7. Notice how the math didn't result cleanly into a whole number. It left us with a stubborn radical. And this brings us to a really vital part of your mathematical strategy, understanding how to present that final stubborn result. Leaving the radical perfectly intact, like negative 3 plus or minus the square root of 7, is what we call the exact answer. If you punch that into a calculator to get decimals, you are generating an approximation. In critical fields like aerospace engineering or advanced physics, exact answers are heavily preferred. Every single time you round a decimal, you lose a tiny fraction of data. Across hundreds of interconnected calculations, those tiny losses can compound into massive, catastrophic errors. Keeping the radical intact? That preserves perfect, undeniable mathematical truth. Tool 3, completing the square. All right, time to escalate things. When an equation is in standard form, has all its required terms, but stubbornly refuses to factor nicely, we reach for completing the square. But watch out, because there is a massive algebraic trap right at the starting line. Our source provides a golden rule for this method. Important, if a does not equal 1, divide all terms by a before proceeding to the next steps. Do not skip this step. If you forget to clear out a coefficient at the front of your squared term, the entire subsequent process is going to collapse on itself. Assuming a is indeed 1, here's how we perform this kind of mathematical alchemy. First, move your constant to the right side of the equal sign. You're effectively leaving a deliberate blank space on both sides of your equation. Next, look closely at your b term. Cut it exactly in half and square that resulting number. Third, add that newly squared number to both sides of the equation to maintain structural balance. Think about what we just did. We artificially force the equation into a state of perfect symmetry, and that lets us factor the quadratic side into a beautiful perfect square. Let's actually watch this elegant transformation play out step by step. We're starting with x squared plus 6x minus 11 equals 0. First, we move the 11 over to the right side, creating those blank spaces we talked about. Now we assess the b term, which is 6. What's half of 6? It's 3. And 3 squared gives us 9, so we add 9 to both sides of the equation. This forces our previously stubborn left side to become a perfect square, factoring cleanly down to the quantity x plus 3 squared. On the right side, 11 plus 9 simply equals 20. And look at that. We now have a scenario ideally set up for our previous tool, the principle of square roots. We take the square root of both sides, simplify the radical, and seamlessly arrive at x equals negative 3 plus or minus 2 times the square root of 5. Just to reiterate our earlier point about real-world applications, negative 3 plus or minus 2 root 5 is our pristine, exact mathematical truth. The radical is firmly intact, meaning absolutely no data has been lost to premature rounding. Now sure, if you're a carpenter cutting a piece of wood, or an architect mapping out a physical space where precision to the 100th of an inch is perfectly fine, you can totally drop this into a calculator and use the decimal approximations of roughly 1.472 and negative 7.472. But always, always know the fundamental difference between the exact truth and a practical approximation. Tool 4, the quadratic formula. Okay, it is time to unleash the heavy machinery, the undisputed master key of all algebra, the quadratic formula. I know, it's dense, and it looks deeply intimidating to a beginner, but it is incredibly powerful. Why? Because it simply does not care if your numbers are messy, ugly, or totally impossible to factor. It will consistently brute force its way to the exact right answer every single time. X equals negative b, plus or minus the square root of b squared minus 4ac, all divided by 2a. It is the ultimate failsafe for any quadratic equation. Deploying this master key is wonderfully systematic, but you've got to be strictly organized on your end. Step 1. Correctly identify your a, b, and c values from your standard form equation. Step 2. Carefully substitute those values into the formula. And I really want to emphasize this. The hardest part of this entire method isn't the calculus of it. It's purely organizational. Tracking your negative signs when you plug the numbers in is where the vast majority of mistakes happen. Keep your ducks in a row. Step 3. Logically simplify the arithmetic under the radical. And finally, step 4. Reduce the resulting fraction to find your final exact answer. Let's physically test this master key on the exact same stubborn equation we just solved. X squared plus 6x minus 11 equals 0. First, we identify our vital terms. A is 1, B is 6, and C is negative 11. We carefully substitute them in, putting mental or even physical parentheses around our negative 11 so we don't lose track of the signs. We square the 6 to get 36, and subtract 4 times 1 times negative 11, which morphs into a positive 44. The math under the radical simplifies perfectly down to 80. The square root of 80 cleanly simplifies to 4 root 5, and when we divide everything by our denominator of 2, look where we land. We arrive right back at x equals negative 3 plus or minus 2 root 5. Notice the profound revelation here. Mathematics is beautifully, undeniably consistent. Two completely different logical pathways led us to the exact same undisputable truth. So you now have a completely stocked and functional mathematical toolkit. You are fully equipped with simple factoring, the principle of square roots, completing the square, and the mighty quadratic formula. The big question you have to ask yourself now when facing a new equation is, which tool will you reach for first? True mastery of algebra isn't just about the mechanical memorization of these formulas, it's looking at the raw equations sitting right in front of you and instantly knowing whether you need a scalpel or a sledgehammer. Keep experimenting, choose your tools wisely to maximize your efficiency, and I'll see you in the next explainer.